Hello students, welcome to a session with Time. Now, this live session continues from where we ended. We had taken coordination compounds. So this is the second part, and coordination compounds belongs to chemistry. So I hope the previous video was useful. You could find good number of questions there, good number of questions that had appeared in the previous entrance exams. We had also mentioned what exam they have come from. And this session continues from where we left. So more questions on this coordination compounds we'll see here. So see to it that you make the most of these sessions. So these are the details of our YouTube channel and the website. For more interesting videos, you can log in. So this session is a continuation of the questions discussion on coordination compounds. Now, if we are ready, we'll start now. Now, the very first session sorry for the small change there. Now, this question is an assertion reason type of question. Assertion says that the total number of geometrical isomers shown by this coordination ion, complex ion, is 3 that we need to check. Then reason says that this complex ion has an octahedral geometry. I think the reason part we can easily make out because En is a bidentate ligand. There are 2 such bidentate ligands, so 4 bonds. 4 plus 2 is 6, so 6 means it is an octahedral geometry. So reason is true. Clear? So sorry. This particular session is on coordination compounds. This is part 2, and this belongs to chemistry. Now, in the previous session, we had discussed some questions from the entrance exams. This session also continues the same. So we'll have even more questions, and we'll check how best we can tackle all the questions, all different types of questions, and see to it that we benefit out of this. So this is a YouTube channel, and these are the details that you can find. And in this, you will find interesting videos, which will be of great help while you're preparing for your entrance exams of whatever type it is, even if it is NEET or JEE Main or any of the exams conducted by the deemed universities, right? Also CUET, BITSAT, right? Now, the very first question is on this assertion reason type. In this, the assertion is mentioned that there are total 3 isomers, 3 geometrical isomers for this complex. Now this complex is CO, En taken twice, Cl2 with a positive charge. Now the reason part I think can be taken up first. Does it have an octahedral geometry? For octahedral geometry, we require 6 coordinate covalent bonds. So 6 dative bonds are required. Now check. Ethylene diamine is a bidentate ligand. There are 2 such ligands. So 2 into 2 is 4, 4 plus 2 is 6. So indeed, there are 6 dative bonds. So it is an octahedral geometry. So reason is correct. Now this won't be correct then. Now let us look at the assertion part. The total number of geometrical isomers shown by this one. Now we shall put it here. If it is an octahedral geometry, we have the central atom, right? That is cobalt. And we could have a Cl and a Cl cis to each other, that is at 90 degrees. And then the En, ethylene diamine, can attach like this to the central atom. So this bond angle is 90 degrees, right? So this is a cis isomer. The next thing that you can think of is an octahedral where the 2 Cls are trans to each other, that is at 180 degrees. And here we'll have an En, bidentate ligand, and here we'll have an En. Clear? So here is the central atom, cobalt. Now this is trans. Now look at this. The trans isomer has got a plane of symmetry, right? So when there is a plane of symmetry, it means that there is no optical isomers for this. There are no enantiomers for this. Whereas if you take the cis isomer, in the cis isomer, there are 2 enantiomers. There is no plane of symmetry. So there are 2 enantiomers possible. So these 2 and this 1 will make up for the 3 that is mentioned there. Correct? So assertion is true. Reason is also true. But then reason is not the correct explanation for the assertion, isn't it? So we find that the cis isomer has got 2 enantiomers because there is a lack of plane of symmetry. And in the trans isomer, we have got a plane of symmetry. Therefore, it is only 1 molecule. So 1 isomer here and 2 isomers there. Total is 3. So we find that the reason is also true statement. Assertion is also a true statement. But then we do not have a connection between the reason and the assertion. Is that right? So the first question is answered. So what is the answer then? So it has to be C. Both A and R are correct, but R is not the correct explanation of A. R is a general statement that it is having an octahedral geometry, right? But then why is this assertion true? This is because the geometrical isomers, that is cis and trans, total have 3 isomers. In the cis, we have 2 enantiomers, and the trans, we have just 1 molecule, 1 compound. Clear? So option is C. Next question coming is an octahedral complex with a formula COCl3NNH3 upon reaction with excess of AgNO3 solution gives 2 moles of AgCl, right? Which means that 2 Cl minus are in the ionic form. Consider the oxidation state of CO in the complex as X. So what will be the value of X plus N? Let us look at the options. Options are there. Now, this particular formula, if you have to convert into the coordination form, I'll write here NH3 taken N times Cl, and then outside there need to be 2 Cls, because when we break this bond, 2 Cls come out as Cl minus. So 2 Cl minus ions in the presence of AgNO3, which gives Ag plus. So 2 Ag plus will give 2 AgCl, right? So 2 moles of AgCl are formed means what? There are 2 chlorines outside. That is part of the primary valency. Primary valency is ionizable, isn't it? So here the value of N we need to find out. It is already mentioned that it is an octahedral complex. So how many bonds? 6 bonds to the central atom. There is 1 bond with chlorine. So N needs to be 5, correct? So 5 ammonia and 1 chlorine will make up for 6 bonds because ammonia is also a monodentate ligand. Cl is also a monodentate ligand. So we find that this N has to be 5. Next, what is the oxidation state of CO in this complex? See here, CO is, if it is X here, ammonia carries no charge. The Cl minus will give you -1 there. And this whole thing is equal to -2 because 2 chlorines are outside. Each chlorine is 1 minus. So X will be equal to, this is 2 and that is 1. So this is 3. This is actually minus of -2. Why? Because the square bracket will have a charge opposite to what the co-ion has. The co-ion is what? Cl minus. There are 2 such Cl minus ions. So if it is -2, the charge on the square bracket should be minus of -2. So this -1 will go to the other side and then we'll make it as 3. And then X plus N will be 3 plus 5, which is equal to 8. X is 3 and 5 is, that is N is 5. So it is option D. I hope this is clear. Simple question it was, right? Oxidation state we need to know. And the number of Cl minus ions present outside, right, will decide how much is the N value. Because it is an octahedral complex, so 6 bonds should be there to the central atom. Clear? Next question. What is the correct IUPAC name of PT-Br2 PME3 taken twice? Now this is trimethylphosphine. This ligand's name is what? Trimethylphosphine. Phosphine is pH 3. But instead of the hydrogens, we have got the methyls. And this is bromo or bromido, right? So we have dibromo. So B you need to look at, and then this trimethyl T you need to look at, and in alphabetical order, the dibromo will come first, followed by the trimethyl, right? And then there are 2 such trimethyls. So already when there is a tri in the name, we cannot use a di here. So it has to become bis. So it is bis trimethylphosphine dibromo, right, attached to the platinum. Now let us look at the names. So di is out, right, and you cannot have a bis for the bromo, right, and then you cannot have this first compared to this. So the dibromo B, that is B for bromine, will come first. So the option is C. So dibromo B here and the trimethyl, alphabetical order. And then when there is a tri here, you need to have a bis. So dibromo bis trimethylphosphine platinum 2. Easy answer. Option C it is. I hope this is clear. Next we'll move on to 3 complexes or 4 complexes given here. What is the correct order of A, B, C and D in terms of the wave number of light absorbed? First of all, let us look at what complexes these are. This is an octahedral complex because 6 ligands are there. Again an octahedral complex. Again an octahedral complex, but then this is a 4 coordinate complex here. A 4 coordinate complex, right, is having lesser energy gap, whether it is tetrahedral or square planar. Now let us look at which ligand is the strongest. Cn is the strongest here, right? So the strongest ligand will give the maximum gap. So this is T2G, this is Eg. So this gap, that is delta O, is maximum. You know the delta O is Hc by lambda, which is equal to Hc into nu bar. So this wave number and this energy gap are proportional to each other. More the energy gap, more the wave number. So whichever has got the strongest ligand, so B will have the greatest wave number between the 2 states, that is T2G and Eg. So the radiation that is taking up a T2G electron to the Eg will require more wave number or more energy in the case of B, maximum in the case of B. So this and this are out because B has to be the maximum. Then followed by B, there are 5 NH3s in both A and C. But then Cl is a weaker ligand when compared to H2O. H2O is a stronger field ligand than Cl. So next to B comes C. Therefore, answer is A. And then next to C will be A. And then finally, you'll have this D. Clear? So option A it is. So more the wave number, more the energy gap. It means that whenever the energy gap is more, so we'll write a strong field ligand leads to greater delta O and greater nu bar. I hope this is clear. Shall we move on to the next question now? Yes. Now this has appeared in JEE Main April 2024. The metal atom present in the complex MABXL, where A, B, X and L are unidentate ligands, means they form only one bond with the central metal, and M is the central metal, that involves sp3 hybridization. What are the number of geometrical isomers exhibited by this complex? So it is sp3. sp3 means it is tetrahedral, right? sp3 means tetrahedral. So we'll have the M here. Let us put the A, B, X and L, right? Let us put another such combination of A, B, X, L. I'll put A here, I'll put an L here, I'll put a B there, I'll put an X here, right? So is this different from this? That we need to check. If it is different, then the geometrical isomers will be there. More geometrical isomers will be there, as many. Now look at this. This A to, let us take A to B bond angle and A to B bond angle here. Are they both same? They are both same. Both will be close to the tetrahedral bond angle of 109 degrees 28 minutes. In fact, all the bonds are close to this, right? Therefore, there is no difference between this and this. They are both the same, right? There are no geometrical isomers in a tetrahedral geometry. Tetrahedral geometry will not have geometrical isomers. Suppose the same thing was in the square planar part. Let us look at that part also. So M, A, B, X and L. Suppose it is like this. And then I have changed, got another form here. Let us say that this is A, X, B and L. Now this is what? This is sp3. sp3 means it has to be tetrahedral. It is tetrahedral. We are looking at the possibility of if it was a square planar complex. Then look at this. AMB bond angle is 90 degrees. Whereas here AMB bond angle is 180 degrees. So there is a difference. So whenever there is a bond angle difference, it makes a geometrical isomer, right? So A to B, right? A to M to B, the bond angle is 90. Whereas here in the second one, the A to M to B is 180 degrees. So these two are geometrical isomers. But then this is not the geometry adopted. This is not square planar. This is tetrahedral because there is an sp3 hybridization. For a square planar, you need dsp2, right? So here there are no geometrical isomers. Option is A. Clear? There are no geometrical isomers. Geometrical isomers are there only for a square planar or an octahedral, right? Not for a tetrahedral. Clear? Next question. This has come out in JEE Main Feb 2024. Statement 1. Dimethyl glyoxime forms a 6-membered covalent chelate. It's a chelate with NiCl2 in the presence of NH4OH. So dimethyl glyoxime is a ligand, is it not? It is a ligand because of the nitrogen atoms. Clear? So let us check the structure of dimethyl glyoxime. That will make it clear. In fact, it forms a ring with the metal. The ring with the central metal is nothing but a chelate. Chelate is a closed ring that forms between the ligand and the metal. Prussian blue precipitate contains iron in both +2 and +3 oxidation states. That is also true. In fact, the statement 1 is also true. Statement 2 is true, right? And what should be the answer then? Both statement 1 and statement 2 are true. but they are not connected. In fact, this is not an assertion reason type. Prussian blue is what? Prussian blue is Fe4, FeCN6 taken 3 times. Now this ion is in the +2 state. I know that 6Cn minus will make it -6. So this entire thing becomes -4. -4 into 3 is -12. And this ion has to be +12. So this is +3 into 4, which is +12. So ion in +3 state, ion in +2 state are both present in the Prussian blue PPT, right? So statement 2 is correct. Now let us check the structure of the complex, right, with nickel 2 plus of DMG. So option is B here. Let us look at the, this one. If you're looking at, this is dimethyl glyoxine. And this is the nickel 2 plus. So this is DMG, right? And here the nitrogens have coordinated with the nickel, central metal. And then if you're taking nickel as atom number 1, this is 2, this is 3, this is 4, 5, and 6. You have a 6-membered ring, so it is a chelate. So chelation has happened, right? A 6-membered ring this side, a 6-membered that side has been formed, right? Similarly, this is a 5-membered and this is a 5-membered. So chelation happens between nickel 2 plus and dimethyl glyoxine. You know that we are using NH4OH. That NH4OH will pull out 2 hydrogens. As you're able to see here, 2H plus. So 2H plus have come out, and then nickel 2 plus has formed a complex with DMG. So DMG is actually 2 minus and nickel is 2 plus. So overall complex has got no charge. I hope this is clear. We'll now move on to the next question, which has appeared in April 2024 JEE Main. If an ion complex, ion what? Ion 3 complex with a formula FeNH3 taken X times, Cn taken Y times with a minus charge has no electron in its Eg orbital. When you say Eg, the indication is that it is an octahedral complex. When it is octahedral complex, you know that X plus Y needs to be 6 because the total number of ligands, because this is also monodentate, that is also monodentate, right, will give you 6 bonds to the central atom. So when the mention of Eg happened, it means that the complex is octahedral. That is indication. And when it is octahedral, right, the number of ligands, number of monodentate ligands is 6. Therefore, X plus Y is equal to 6. Option A it is. I hope this is clear. I think this is the simplest so far. Shall we move on to the next question then? Yes. Now, this is match. In list 1, we have the complex given, and in list 2, we have to find out the type of isomerism. This has come out in NEET 2024. Now, look at the first one. There is an NO2. NO2 can also be considered as ONO, means N, 2 O's and 1 N. The nitrogen can be the donor or oxygen can be the donor. So A can give a linkage isomerism. 2. In fact, A can also give ionization isomerism because one chlorine can come in and one NO2 can go out. But then linkage is not there in any of the other options, B, C, and D. So we'll take A for linkage isomerism, right? Then look at this B bit. A bromine can go inside as bromide. A sulfate can come outside. So this is ionization isomerism. So this is 3. And then this is one coordination sphere. This is another coordination sphere. So this is coordination isomerism. So this is 4. And then this one, a Cl can go in and a H2O can come out. So it's a hydrate or a solvate isomerism. So this is 1. Let us look at the options. 2, 3, 4, 1. 2, 3, 4, 1 is there in option A. I hope this is clear, right? So just to note that A can also be ionization isomerism. A is both 2 and 3. But in the remaining complexes, we do not find any linkage. Therefore, this linkage has to go for A. Clear? Next question. Now we have a complex ion and then its hybridization we need to find out. All right. So this nickel with 4 cyano, right? Cyano is a powerful ligand, strong field ligand, and nickel is in +2 state. So it is D8, right? And then if you're able to see the nickel, it's a square planar complex. So you cannot have so this and this. So D8, 1, 2, 3, 4, 5, 6, 7, and 8. So 1D is available. So that D can combine with 1S and 2P and give DsP2. So this is option 4. This is 4. So this is a square planar complex. COF63 minus, cobalt is in +3 state and fluorine is a weak field ligand. So weak field ligand and it is octahedral. So T2G and EG. So CO is D6, 1, 2, 3, 4, 5, 6. So no inner D is available. So it is only outer D. Outer D means sp3 D2. So this is what? This is 3. But then oxalate is a strong field ligand. So it will pair up the electrons in the T2G. So 1, 2, 3, 4, 5, 6. Cobalt is again D6 here. Cobalt D6, cobalt D6. But here it is a strong field ligand. So 2 Ds are available. So it can make D2sp3, inner D. So it is 2. And then you know that Cl is a weak field ligand. It cannot give square planar. It gives a tetrahedral. Tetrahedral is 1. That is sp3. So what are the options? Let us look at them. 4, 3, 2, 1. 4, 3, 2, 1 is there in option A. I hope this is clear. Understood? So this is again a matrix match, a match between list 1 and list 2, which has come out in NEET 2024. Next, NEET 2022. Complexes are listed and you need to find out the type of isomerism. Now look at this. There is an NO2 given here and an ONO. So this is linkage isomerism. So 3. Then you have the coordination spheres, right? Cobalt with NH3 and the same cobalt is now with Cn. So the ligands have been exchanged between the central atoms. So it is coordination isomerism. So 2. Then what is this third one? A Br can go in, a sulfate can come out. That is what has happened here. So they are ionization isomers. So this is 1. And then here a Cl can go in, a water can come out. So it is hydrate or solvate. So this is 4. So 1 hydrogen, 1 water has come out and 2 Cls are outside, which will hold this H2O. So 3, 2, 1 and 4. Option D it is. I hope this is clear. Yes, as many different questions that we take up and then understand, so much of usefulness you'll find in the exam, because when you're actually taking the entrance exam, you're writing the entrance exam, you will not find that the question is something new, because a similar question we had already taken up for our practice, and then we had sufficient practice, and then we have sufficient tests taken up, right? You can test yourself. You can take these questions and then at random, you can start solving. So that will be of great help. Next question, NEET 2022. The order of energy absorbed. So it is simply what are these? These are 6 coordinate, 6 coordinate, 6 coordinate. So it is octahedral. Octahedral means the gap between T2G and EG. If it is more, that is what is the energy gap, energy absorbed. So where is the gap more? Whenever there is a strong field ligand. A strong field ligand leads to more delta O. Now check. Which one is the strongest? En is the strongest. So C will be the maximum, followed by, there are two ENs here, there is only one EN there. So C is greater than A is greater than B, correct? So it has to be option A, C greater than A greater than B. So shall we say that the wave number also has the same order? Because wave number and the delta O are proportional to each other. That's what we have seen in the previous. But then lambda is opposite, because you know that nu bar is 1 by lambda. So for lambda, it is just the reverse there. So it will be B greater than A greater than C. There will be option B then, is it not? Next question from NEET 2021. Ethylene diamine tetraacetate. When you say tetraacetate, it means that there are 4 such CH2COO minus units. And it's ethylene diamine. So N, C, C, N, and then on the N we have CH2COO minus, CH2COO minus. Here also we have CH2COO minus, then CH2COO minus. Nitrogen will donate. The 2 nitrogens can donate. This is CH2, this is CH2. The oxygens can also donate because it is tetraacetate. So these are all the parts of acetate, acetic acid's acetate ion. So this part is 4 in number. So this can act as a donor, this one, 3rd, 4th, 5th, and then 6th. So it's a hexadentate ligand with 4 oxygens and 2 nitrogens as donor atoms. I hope this is clear. Option C it is. Next question. Again, match between the complex given and the shape and magnetic moment. So there are 2 more things taken up in list 2. 2 things taken up in the list 2. Nickel tetracarbonyl will have nickel in the 0 oxidation state, right? And this is tetrahedral and it is diamagnetic. Diamagnetic means the magnetic moment is 0. So where it is? Tetrahedral diamagnetic means it is 3. Option 3. Diamagnetic means magnetic moment is 0. Whereas this we have seen is square planar, right? Square planar, and then we have still no unpaired electrons, so it is diamagnetic. Square planar and 0 BM is 2. This we have seen is sp3, so it is tetrahedral. Look at that, nickel is in D8 system. So D8 with chlorines as, sorry, this is for octahedral I have drawn. Let us move into the tetrahedral form. In the tetrahedral form, we have 2 down, that is E, and then 3 up, that is T2. So this is T2 and this is E. And it is Ni with D8 configuration. So 1, 2, 3, 4, 5, 6, 7, 8. So 2 unpaired electrons are there. So it has to be option 1. 2.8, is it not? Root of 2 into 2 plus 2 will be close to 2.8, 2.82, is it not? And what about the D bit? D bit, we have got Mn in the +2 oxidation state. So it is D5. Mn is D5S2. It is already in the +2 oxidation state. So D5. Br is a weak field ligand. So it is again the same, 2 down, 3 up. D5, 1, 2, 3, 4, 5, right? So it will be 5 unpaired electrons. So root of 5 into 5 plus 2. So that is tetrahedral and then 5.9. So this is 4. So 3, 2, 1 and 4. 3, 2, 1 and 4 is option C. I hope this is clear. Yes. So another different type of question between the complex and the shape and magnetic moment. Next, the number of species that are involved in sp3d2 hybridization. Now we know that NH3 is a strong field ligand and cobalt is in +3 oxidation state, so it is D6. And this is octahedral. So T2G down, Eg up, and all the electrons are paired up. So 2 Ds are available for hybridization. So that will be D2sp3. So this is not the option. SF6 is simply sp3d2, that you know very well because it is not a complex. So it is sp3d2. Then what about CO? CO here is again +3 oxidation state, but then this is a weak field ligand. So that I am putting it here. So D6, 1, 2, 3, 4, 5, 6. So there is no D available, right? Inner D is not available. So it will be sp3d2. So this will give you sp3d2. This will give you sp3d2. What about this one Cr with +3 state? Cr is d5s1. So in +3, it is d3. So 1, 2, 3. So 2 d orbitals are available. So it will undergo d2sp3. So this is not the case. What about Mn in the +3 state? Mn in the +3 state is d4. 1, 2, 3, 4, 5. d4. 1, 2, 3, and then 4. There is only one d orbital present. So you cannot have 2 d orbitals. We require d2sp3, but there is only one d available. So this will undergo sp3d2. Then what about MnCN6 3 minus? This is a strong field ligand. This was a weak field ligand, right? And then the same thing, I'll put it here down. 1, 2, 3, T2G, and then Eg. So Mn is in +3 state, so D4. So 1, 2, 3, and then 4. So 2 Ds are available. So it is D2sp3. So this is not going to give. So how many will give? 1, 2, and 3. Option B it is. Clear? Shall we move on to the next question now? I hope you're noting. Yes. Again, a list here with the complex given, and you are required to give the primary and secondary valency. Primary is nothing but the oxidation state that you need to find out. This is the number of dative bonds that we need to get. Now here, I think we'll do the secondary valency first because it is easier. There are 2 bidentate ligands, so 4 bonds from there, and 2 bonds from this monodentate ligand, so it is 6. So 6 I'll write. Next, look at this Cl. This Cl is 1 minus. So if this cobalt was having an oxidation state of X, En will not offer any charge, but there are 2 chlorines inside, and that whole thing should be equal to minus of -1. So it is +3. So 3. So 3 and 6. So this is option 1. Look at the next one. How many ligands are there? 2 plus 1 plus 1, 4. So only 4 is the secondary valency. And then platinum is having no charge, 0 on the complex. NH3 will not offer any charge. 1 charge from Cl, 1 minus, 1 NO2 minus. So platinum is in +2 state. So 2, 4. 2, 4 means option 4 here. Means the list is 4th one there. And then here, cobalt is with SCN taken 4 times. Each SCN is 1 minus. So this is 4 minus. And if there is one Hg outside, if it is 1 plus, the cobalt will be 3 plus. So I'll write 3 here. And there are 4 such ligands, monodentate. So 3, 4 means this is 2. And then here Mg is in +2 oxidation state. And EDTA forms 6 bonds. It's a hexadentate ligand, is it not? So this is option 3. 1, 4, 2, and 3. Option C it is. I hope this is clear. Primary valency you have checked. We have checked even the secondary valency in the form of dative bonds. Primary valency in the form of oxidation state. I hope this is clear. Next, again, a match between the complex, and now we have hybridization and magnetic character. Now this MnBr4 2 minus, we have already seen manganese is in +2 oxidation state. It is D5. So 1, 2, 3, 4, 5. This is tetrahedral. So D5, 1, 2, 3, 4, 5. So this is sp3, shall we say, and it is also paramagnetic. So this is 4. Then FeF6, this is octahedral. So we'll put octahedral, 3 down, 2 up. And then it's a weak field ligand. Fe is in +3 oxidation state. 1, 2, 3, 4, 5. So it is sp3d2 and then paramagnetic. So this is 2 here. And then the third one, we have a strong field ligand here, and this is diamagnetic. We have already seen in one of the previous questions. So cobalt is going to give a diamagnetic complex, and this is inner orbital complex. So it is D2sp3 and then diamagnetic. So it is option 1. And nickel tetracarbonyl, we have already seen it is sp3, right? And it is also diamagnetic. So it is option 3. So 4, 2, 1, 3. 4, 2, 1 and 3 is there in option C. Clear? So different types of questions, right? Different connections being asked, isn't it? Now again, a match of complex and hybridization, only hybridization of the central atom, central metal. Now cobalt is in +3 oxidation state and it's a weak field ligand, right? Therefore, there is no inner D available. So it is sp3d2. So 3. You can check that. NiCl4 2 we have just now seen it is sp3. So it is 2. Cobalt is in +3 oxidation state, D6 configuration, strong field ligand, and therefore D2sp3, where it is option, this is 1. And then this we have seen it is square planar, so it is dsp2, where it is 4. So 3, 2, 1, 4. 3, 2, 1, 4 is option D. I hope this is clear. Next question, which has appeared in Jan 2025, JEE main. 1 mole of an octahedral complex gives 3 moles of ions on dissolution in water. So 3 ions come out. 1 mole of the same complex reacts with excess of AgNO3 to give 2 moles of AgCl, which means that 2 Cls are waiting outside. Right? So 2 Cls are inside, means the inside will be what? Outside means the inside will be CONH3 taken 5 times and then 1 Cl. Right? Structure of the complex is option A. Correct? 3 Cls are there. 2 Cls are there outside because they are ionizable to yield 2 moles of AgCl with AgNO3 excess. And then 1 Cl is inside. And there are 5 NH3s because it is an octahedral complex. So 6 bonds need to be there to the central atom. Clear? Option A it is. Next question. The correct order of the following complexes in terms of their crystal field stabilization energies. Now, let us check if all these are octahedral. Only this 4 is not octahedral. Remaining are all octahedral. Now, in octahedral, you know that there is greater, that is delta O is greater. We know that delta T is only 4/9 of delta O. So the, what shall we say, tetrahedral or even square planar is less than the octahedral. Now let us look at which is a strong field ligand. You know that En is a strong field ligand, right? So En will give you the maximum gap. So crystal field stabilization energies, if you're looking at octahedral, this is minus 0.4 delta O, that is plus 0.6 delta O, right? And a strong field ligand is going to give all the, this is D6 configuration with 6 electrons in the T2G. So 6 into minus 0.4 is minus 2.4 delta O. Maximum negative means maximum stabilization. So En is the strongest ligand, right? Followed by NH3. And NH3 6 times is better than NH3 4 times, right? Then the metals oxidation state also matters. The +3 will be giving a more stable complex than +2, means it will give more delta O. And the 4 coordinate is less than the 6 coordinate. Based on all these things, let us check. So this inside cannot be allowed, right? So B and D are out. So CO En taken 3 times with 3 plus is better than NH3 6 times 3 plus, better than NH3 6 times 2 plus, and then so it is option A. This is 4 coordinate. These are 6. And we said 4 is less than 6. And you know that this is 2 plus and that is 3 plus. So plus 3 is more than plus 2. So plus 2 is less than plus 3. Option A it is. I hope this is clear. Next question, which has appeared in JEE Main April 2024. A first row transition metal, that is 3D series, in the +2 oxidation state has a spin-only magnetic moment of 3.86, which means that there are 3 unpaired electrons, correct? What is the atomic number of the metal? Now, 3 unpaired electrons. So look at +2 oxidation state. All these are what? D1s2, D2s2, D3s2, like this. So s electrons we need to remove, because +2 oxidation state, you know that the first 2 electrons are removed from the s because s is on the outside, because it is a 3D and it is a 4s. Whichever orbital is outside, from there you remove the electrons. So s electrons are gone, and we need 3 unpaired electrons. This is atomic number 21, this is atomic number 22, atomic number 23. Scandium, titanium, and this is vanadium. So option B it is. Clear? Next question. 2 statements are given. A solution of NiH2O6 times 2 plus is green in color. True, that you need to know. And this square planar complex is colorless. Yes, because the absorption happens in the UV region, and that absorption happens in the visible region. So it is green in color. So it takes in red and then gives out green. Both the statements are true. Option B it is. Clear? Next question. Again, list 1, list 2. Now electronic configuration. So Cr is in +3 oxidation state. That will put it here. Let us also have this. So Cr is in +3. Cr is what? D5s1. So it is octahedral. So T2G down, Eg up. And then this is a weak field ligand. But Cr is in +3 state, means that it is D3. So 1, 2, 3. So it is T2G3, Eg0. Where it is? 2. Then look at Fe with +3 state. It is ferric, D5, and it is a weak field ligand. So D5, 1, 2, 3, 4, 5. The second one I'm putting here, 1, 2, 3, 4, and 5. So this is T2G3, Eg2. So this is third. Ni is in +2 state, so it is D8. And H2 is a weak field ligand. In fact, all are weak field ligands, all are water molecules here. So third one I'm putting it here. D8, 1, 2, 3, 4, 5, 6, 7, 8. So T2G6, Eg2. So it is 4. And then vanadium. Vanadium is what? Scandium, titanium, vanadium. So it is in the D2 state, because vanadium is D3s2. And we've removed 3 electrons. S2 is gone and 1 from D2. D3 is also gone. So it has become D2 now. So D2, that I'm putting it here, 1, 2. So T2G2, Eg0, where it is? 1. So 2, 3, 4, 1, where it is? 2, 3, 4, 1 is in option C. Clear? Next question, which has come out in JEE Main Jan 2024. The strength of anionic ligands can be explained by crystal field theory. So then why is OH minus weaker than H2O then? There is no explanation. So this is wrong. Cannot be explained. In fact, Cn minus is less than CO. CO has got no charge. Even Cn minus, right, is better than an anionic ligand with a negative charge 2 minus. Possible. So S2 minus, if you're looking at O2 minus, you're looking at, it is less than Cn minus. So it means that the anionic ligands, the strength of those ligands is not explained by crystal field theory, because crystal field theory looks at charges on the ligands. Clear? Valence bond theory cannot explain a quantitative interpretation of the kinetic stability of coordination compounds. Correct? Hybridization in NiCN4 2 minus for nickel is DsP2. Correct? The number of possible isomers for this is 1. No, this itself will give you enantiomers, a combination of enantiomers. So this is PT. The two CLs can be trans to each other, but this is cis, he's saying. So Cl, Cl, and this is a En, and that is a En. This does not have any plane of symmetry. So you'll have an object, you'll also have an image. Therefore, it cannot be one. It is actually two. There is a plus isomer, there is a minus isomer, right? We don't know which is plus and which is minus. So if the object is plus, the image will be minus. So this is not correct. So B and C, option A it is. Clear? Next, look at this. S2 minus is less than SCN minus. So the charge is not going to matter, is it not? And C2O42 minus is going to be less than NCS minus. So even that is not going to matter. So the charges are not going to matter. So crystal field theory doesn't explain the strength of anionic ligands by looking at the charges. Clear? So this is the spectrochemical series. Next, January 2024 question. In which of the following metal carbonyls CO forms a bridge between the metal atoms? It is found only in D, right? In D, you'll have, let us look at the structures. So it is option D. So A and B are very, very similar. They form a triangle between the OS, OS and the OS, right? And then here, so 12 is to be divided. So 4 there, 4 there, and 4 there. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 of COs. Same thing for A and B. This Mn is also not having. So Mn bond will be there. And then you'll have CO, 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 and CO, right? But what happens in this is the formation of a bridge. Let us look at that. Option D it is. So this is the first triangle we talked about. Whether it is osmium or ruthenium, it is the same. Next, again, Mn, Mn, you do not have any CO bridge between the Mn and Mn. But here you will have, these are the bridges. Clear? So CO here and a CO there are forming a bridge between the two COs. Clear? Now, since we have got this, let us discuss about what is effective atomic number. For this complex, we are going to do effective atomic number. Effective atomic number is atomic number of the element minus its oxidation state plus electrons gained from the ligands. We'll do it for this CO. CO's atomic number is 27. And here, in fact, most of the carbonyls, the oxidation state is 0. And how many electrons are gained, that we need to check. I'll take a different pen here. Yeah. This is a ligand and a ligand. So ligand gives 2 electrons. So 2, 2, and then 2. Here. This is a normal covalent bond, normal covalent bond, normal covalent bond. So cobalt has gained only 1 electron here, 1 electron, and 1 electron. But here from the ligands, it has gained 6 electrons. So we'll write here plus how many electrons are gained? Ligands or other atoms to which it is connected. Now ligands will give 6. 3 ligands are there. And then 3 from 3 covalent bonds. If it is a dative bond, it will be into 2. If it is a normal covalent bond, it will be into 1 only. Only 1 electron is gained here. So how much is 27 plus 9? It is 36. 36, you know, is the atomic number of krypton, which is a noble gas. So effective atomic number shows that a metal has a tendency to get to a noble gas configuration. That is what is the basis of the formation of complexes. So complexes will see to it that the metals become more stable. So you got an atomic number of 36, which stands for krypton, which is a noble gas. So cobalt gains this noble gas configuration by accepting or forming bonds with other ligands or other atoms. So here the CO, CO and CO, they have formed dative bonds. So they have given 2 electrons. They are electron pair donors. Whereas other bonds are all covalent bonds. It's only a sharing. So in the sharing, the cobalt gets 1 electron from each bond. So that is how it was 3 from covalent bonds, 6 from the dative. Together, it has made 36. I hope this is clear. Yes. Just one more question before we end this session. Yes. Ethane 1,2-diamine is a chelating ligand. Do we agree? Yes. Because ethylene diamine it is. So CH2, CH2, NH2, and then NH2. This with its electron pair, this with its electron pair can bind to the metal. And this is nothing but a chelation. Formation of a ring is nothing but chelation. Statement 1 is correct. A is correct. Metallic aluminum is produced by the electrolysis of aluminum oxide, that is Al2O3, alumina, in the presence of cryolite. Yes, because we need to bring down the melting point. This is a part of metallurgy. Right. Then cyanide ion is used as a ligand for the leaching of silver. You want to get silver. This is again metallurgy of silver. So what we do is we take silver sulfide, treat it with NaCN, and this forms a complex, right, where Ag is the central atom. Plus how many? You'll have 2 of this, and then you'll have Na2S. Clear? So this reaction will make silver, right, form a complex here. So it is leached. So Ag2S is leached into the complex. This complex is water soluble. Now we are going to add zinc. When zinc is added, zinc gets inside and silver is out. So zinc will give you Na2, Zn, Cn taken 4 times, and the 2 Ags are out. This is how the silver is obtained in the pure form by the cyanide process, which is also called the MacArthur-Forrest cyanide process. Now, this is the leaching of silver. In the leaching of silver, cyanide ion is being used. Yes, correct. Right? And zinc is going to bring the silver out. In fact, this reaction is a reversible reaction. Therefore, you need to add oxygen to make the reaction irreversible. Right? This Na2S will convert into its sulfate, and therefore the reaction becomes irreversible, and you get more and more of the complex. From more and more of the complex, you'll get more and more of silver when you add zinc. So C is correct. Phosphine acts as a ligand to the Wilkinson's catalyst. Wilkinson's catalyst, you know, is used in the hydrogenation of alkenes, but then it is rhodium, chlorine, and then triphenyl phosphine, not simple phosphine. So D is wrong. The stability constants of Ca2 plus and Mg2 plus are similar with EDTA. No, Ca2 plus forms a more stable complex with EDTA because Ca2 plus is bigger. This is Mg2 plus. Make the change there. So Ca2 plus forms a more stable complex with EDTA because of its greater size, so that it can get accommodated in the EDTA. So EDTA complexes cannot have same stability constants. They are more for Ca2 plus complex, less for Mg2 plus complex. So E is also out. So it is A, B, and C. Clear? So with this question, I think we have done 25 questions. I hope we have done as many questions as possible that can come from the coordination compounds. So you should not find it difficult to track any question that comes on coordination compounds, right? I am not saying that it is a full stop on this. There is no full stop. We have tried as many as possible, right, in the 2 sessions that we had. So I hope you have benefited from the session, right? Initial few minutes, we would have found some problem there because there was some problem with the PPT. So I had to redo it, means make the necessary correction there, and the first few minutes have got lost, right? Sorry for that once again, but see to it that what all questions we have done today and the questions from the previous, you will find it in the YouTube videos. are taken up and then you've understood, and then you can redo it, right? Take the questions on your own and then start solving them. I hope this will be useful one, right? Like this, there are many more videos, right, coming your way. So see to it that you make the most of these sessions. So option is D here, A, B, and C. So the particulars once again, right, before we say goodbye. Thank you. Best wishes.